So I'm here with Jason in the SEG Magnetics lab, and we're going over that demo SEG system, and now we're spinning the stator.
So what we have here is the conductor band, just like we have over there on the SEG Mock-up. It is designed specifically to demonstrate a particular aspect of this technology. John would say, it lasts forever, there's no wear. Well, we're going to prove it. We're going to find out why. And we're going to take one of those rollers, pin it over here. We're going to rotate the conductor band. We've got that relative motion going on, and this unit will allow us to isolate and demonstrate the principle that indeed the parts don't touch. If you look in between, it's not touching the surface. So what we've done is proven what John has always claimed, that there is no wear in the device and there is no noise because the parts don't touch. This is what we call proof of concept. You can actually feel the forces. And this is just a copper band. There's no magnetics involved. When I first did these experiments, the rollers did not spin. John also described this. It orbits, it spins. But what I found is, oh, wait a minute, you got to induce the magnetic waveform on it. So we simulated the waveform into it, and bam. Now, not only do we have a roller that floats, it also spins without touching. Over there, you saw that the rollers do spin because they're touching the surface, but here they're not. So again, we've proven another observation that John made in the past.
It's awesome,
huh? Keep going, right? It's not a light force. And keep in mind, we're dealing with relatively minor forces. We're just trying to prove the concept, but when a prototype is operational, they're very powerful forces.
Right.
But it's enough to show that it does do this and that.
It would make sense to work based on the quantity of aluminum copper to slow down the experiment to take out aluminum copper that same kind of lag is going to cause.
There are eddy currents interactions taking place. In the industry, you try to eliminate eddy currents like it's a parasite, but indeed it's our friend, and it works perfectly with the SEG.
It's actually a train levitation system. They use an aluminum. No, it's different. They use an aluminum track, and then there's spinning magnets. And the spinning magnets allows the train to levitate on an aluminum track rather than steel. Same principle.
It still feels the magnetic force from all the way up here. It's interesting.
Yeah, that eddy stands out.
Yeah.
But that's, again, just a copper ring. It's just behind the big stator, or the big ring.
The vibration is the bounce that you get in the outside field.
Yeah.
Because the copper band's moving. It's almost like you're pushing it down through that tube, but
rather spinning it around the tube.
Same difference. Right. But yeah, it makes sense that it would do this.
Yeah. And look, it's still doing it out here.
Sure.
And these have relatively small velocities and compared to the operational mode of the SEG.
And the RPM is related to its distance from here, as you'd expect. So the further you go out, the slower this is going to rotate. See that? Now it's slowing way, way down.
That's awesome.
Because the amount of force...
What's the guy here? He has something else.
I'll show you the other one here. Now, in this one I
got it to lock.
It's okay. Let them discuss.
That's okay.
Okay, go ahead.
In this side, we have magnets incorporated with the copper spinning. So you can take this strong neodymium magnet, and this wants to attract to the ring, but at the last second, you can feel it does not want to push, so it
Right.
has an equilibrium. So you can take and feel this.
Does he have an attraction?
It gets into that.
Is it the right polarity? Does he feel the attractive
Yeah.
impulse?
Yes.
So it wants to attract, but the last minute it repulses.
Yeah.
Yeah.
You can feel that and then describe what
It
you're
drops
feeling.
into that sweet spot.
So it wants to attract to the ring, but the eddies want to push it away, so it meets that equilibrium, creating a little gap between the roller and the stator.
That's awesome.
Yeah.
Oh, yeah.
Oh, yeah.
You feel attraction and a certain repulsion. That's another function of this design. And in other words, it finds an orbit. You can see how all these forces are working together to make for this general, as was observed and described it by John.
Kind of confirmed.
Yeah, it's a proof of concept.
That's really interesting.
So now we know why the rollers will stay on track,
Right.
not touch the surface, and yet counteract the centrifugal force.
Yeah, that's awesome. It wants to grab. So the wheel's slowing down as they go close, right? Like right there?
Because you're getting magnetic drive.
Right there.
If
It's
you're adding a force.
right there. It's nice.
But if you just leave it, it wants to meet that equilibrium. But that's just north-south. If that has the wave, it would spin while it would levitate. Right now you're just getting the levitate, but it's not, you don't experience the spinning through your fingers, right? It's just a push.
Now,
I wonder if that would teach us.
something.
I wonder if that would teach us something about making electric motors.
It wouldn't, you could feel it, you could just feel it repel.
Right. But it will repel. It's
Yeah,
not-
oh yeah.
You see the problem with this uniform magnet, it doesn't spin, you just feel the repulsive force. And the solution was to put a waveform on it like it should be, and then you get your spin. So that was the key to that. Again, that's proof of concept, verification that indeed these things do happen.
Oh wow, that's really
It does
interesting.
not want to touch.
That's the principle of that magnet technology is that.
Oh man, you can
And the
feel.
nice thing about it
Yeah,
is
flip
that
that other way
it will
first.
actually stabilize
Yeah.
in a central position.
That's really weird. Feel this. Just go like this, and you can feel that. You can feel that energy.
Flip that around if you want to feel the attraction and then the repulsion. So hold that tight.
That's awesome.
That way it doesn't matter. You can switch
Right.
it any other way.
And you don't get the same. No, you still get slowed
Yeah,
down.
you
of
get the
course.
repulsion.
Now you notice it causes drag. Okay, but with this design with the SEG, because you have a waveform on it, it's more like a pebble skipping over a surface of a lake. It's skipping over it rather than braking, which is what conventional applications do. They use it like a brake.
But actually,
With this technology,
This is-
we're actually skipping off the surface and not creating any braking action.
In fact, it's very
That-
similar to the dam busters,
Um,
where they build a rolling bomb.
That's
so it's
interesting.
Not just skipping; you're actually rolling as you skip.
Right.
Yeah.
look.
And that's the right way of doing it.
Yeah.
Because we're not trying to break anything, it doesn't break it. That's, again, it goes to show this design is workable. So it doesn't break itself. But a lot of experts think, oh, it's eddy currents, it's going to break. No, it doesn't. They just don't know any better, but they think they do. So we have to educate them.
I'm reminded of saying by Forrest Gump, that great philosopher.
Now this
It
one
a
is.
stupid guy.
This one's a magnetic ring. Does it do anything?
And notice it picked up speed.
I gotta get going, guys.
Okay.
All right. Yeah, we should go soon too.
Thank you very much.
Absolutely.
Thank
Don't
you.
forget to show the viewers this last demo, though, and also the.
Okay.
We still have two more
Oh, yeah, 2 more
demonstrations.
demos, actually.
Okay, Jason.
All right.
See you.
Have an awesome day. Awesome
See ya.
evening. I will see you see you soon. Nice to meet you.
Yes.
you.
So the next demonstration unit is specifically designed to show and help us understand why should the rollers move when there's electrical power radiating out. Well, the way I understand it now is that as electrical currents go through the rollers experiences a force.
It's the right-hand roll.
Yeah. And it gives the rollers electromotive force.
It's an inversion of what you see in a motor. It's the exact same.
Yeah. And so what we're going to do, and the way the SEG operates, the electrical currents go through the atmosphere, they're emitted, and wind up back in the center. But the important thing is we want to know what's happening to the rollers, what forces are experienced. And that's what we have over here. We simulate a roller here. All we're interested in the currents. Currents are going from the plate through the wire and back to the center again.
Okay.
It's an energy cycle. What will these currents on the roller experience when you pump electrical currents through these rollers? And we'll demonstrate it right now. As you can see, and this is just DC. Unlike conventional motors where you got to flip the currents back and forth or use reversing through commutation, this is just pure DC. It can even be pulse DC. Now we've proven right here that it does have motor actions. The rollers will orbit. They will get these forces around. They will spin. They will do all that. There will be magnetic bearing. And then you see that this is a workable design after all. And it's actually sophisticated. It's not a simple thing. There's a lot of things going on electromagnetically.
Pardon me on this one. Is this similar to a homopolar motor here?
It's a unipolar mode.
Okay.
Unlike conventional motors, which they use, pose. They oppose it, then they gotta go flip the currents, reverse it in order to make the bar move around. And that makes sense for this design. It makes it more robust. It gives it unlimited power. Unlike a conventional motor where you got a flux going through a steel core or iron core, that's the limitation. There is no limitation here because air is the media.
I see you have large cables on this. I know it's a demonstration. Is this thing pulling some amps through here?
It sure is. We're applying 1 volt in heavy currents.
How much amperage do you believe?
I think about 160 with 1 volt.
Okay.
So what this does, again, proof of concept that it is workable. The project next needs to focus on the magnetics and the detection of emissions that'll help us do all this. So now we established and proved that all these functions are available in this design. Now we just need the power emanating from the plate as the rollers come about. And that's what we need to do next, is work on the magnetization, come up with a fully programmed set of rollers and a stator plate. And then we know for a fact that these things will happen. We've proven it. So that's the way this program works. We do things step by step, make sure we got our feet on the ground, and apply engineering, the physics, and electrical principles that are inherent in a generator. So we're taking the mystery out of it. We're not dealing with a lot of mysteries at all.
Sure.
And that's the way we make progress here.
They're very logical process.
I like that.
Yeah. Nice work.
Okay. This last demonstration unit is where we're headed to next, and that is to prove that you can impress waveforms on a magnetic material, in other words, a magnet, instead of just north-south, which is what the industry does.
Mm-hmm.
Plug in here. This is a unit I built specifically to scan a magnetized magnetic ring. This is a Gauss meter probe. The Gauss meter probe reads it, sends the analog signal to the digital scope, and there's the sine wave right there. Again, proof of concept that the man's claim, his observational test, is a fact. And that waveform is, by the way, what gives us spin over here. There's a lot more to it than that, but you can see the physical effect of it. It all works together. So this is what ferromagnetics is focused on. We're going to be doing the magnetization of the magnetic components. That's know-how that stays in-house. The industry does not do it. We're the only ones that are focused in developing this phenomena. And it is repeatable. It even has subcarrier waveforms right here. You can see this being repeated.
Mm-hmm.
That's not something you can induce by induction. It is an electronic spike, like a frequency, a high frequency spike. Now we need to work on that and keep making smooth, a smooth sine wave. But that's okay. The point is, we've proven that indeed we can manifest these waveforms, even though it is a north-south programming.
Can I touch this? I'm just going to put a little baby pressure on. Not a lot.
It's a delicate probe.
Yeah, I'm just barely pushing it. It's undeniable, that's for sure.
So the evidence is overwhelming. The SEG concept has merit. I've investigated child surf for 20 years now. Everything that I've investigated has been positive, and that's why I recommend anybody to support and join this business venture is what it is.
Well, like I said before, and I'll say it again, you have my support.
Well, thank you very much.
Anything that I can do to help you guys out,
Great
including
having you here.
donating my time for machining and helping you out, is not a problem. But this is awesome. So, thank you once again. Have a good day.